Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of Mind Maps, we'll be dealing with the sixth chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Electromagnetic Induction. Now, as usual, we'll be enlisting the help of a mind map to explain this chapter. Mind maps are really good tools in order for last-minute revisions. However, like this one, they can be very extensive, so this video is devoted to explaining it in some detail. So, without further ado, let's look and dive into our chapter, which is electromagnetic induction. Now, when you hear electromagnetic induction, you know that this name is connected with electricity, magnetism, and induction, where induction means to generate something. So, what is electromagnetic induction? Electromagnetic induction is a phenomenon in which the electric current is generated by varying magnetic fields. So when a magnetic field is passed through a current carrying conductor, there is an induction or a generation of a current inside this conductor, which is then taken out. And electromagnetic induction is the cost-effective way to produce electricity, and most of our energy systems around the world use electromagnetic induction. It is also used today in wireless charging devices. Now, when it comes to the history of electromagnetic induction, the term electromagnetic induction and the science behind it was developed by Michael Faraday of England and Joseph Henry of the USA. So they independently discovered electromagnetic induction and performed experiments on it. And it was also mathematically described by James Clerk Maxwell, who is a giant in terms of electromagnetism. He was the person who united electricity and magnetism. And when it comes to this chapter, today we'll be dealing about the Faraday's law of electromagnetic induction. We'll be looking at Lenz's law. We'll be looking at induced current, induced EMF, which includes motional EMF and EMF in a circular conductor. Then we'll look at eddy currents, and then we'll look at self-induction, mutual inductance, and self-inductance of a long solenoid. And finally, we'll look at the quantities based on electromagnetic induction inside a rectangular loop, where all of this works. And when it comes to electromagnetic induction, it is dependent on a quantity known as magnetic flux. And so what is this magnetic flux? It is represented as phi b, and it is defined as the product of average magnetic field and the penetrated area of the magnetic field lines. So the formula here, phi b, is equal to B dot A, which is BA cos theta. And the unit of this quantity is in Webers. And when it comes to magnetic flux, it is 0 when the area is 90 degrees with the magnetic field, and it is maximum when the area is 0 degrees with the magnetic field. So now that we've discussed about electromagnetic induction in some detail and gave an outline for what we are to study in this chapter, let's jump into the first topic that we'll be looking at, Faraday's laws of electromagnetic induction. We know that Michael Faraday is the granddaddy when it comes to electromagnetic induction and experiments on electricity and magnetism. He was a giant among experimenters. So he devised two laws for electromagnetic induction. They're basically the same law in different statements. So in order to look at this law, he put a current carrying coil and passed it through a galvanometer. And then he put a magnet, bar magnet with north and south poles, and he moved this magnet towards the coil. And then he noticed that the galvanometer was deflecting, which means that there is a production of current in the magnetic field. And this eventually was found out that this current produces an EMF, which in turn opposes the motion of the magnetic field. But more on that later. So the first law which Faraday has proposed, it says that whenever magnetic flux through an area bounded by a closed conducting loop changes, an EMF is produced in the loop. So because of the change in magnetic flux due to the bar magnet, there is production of current because electricity and magnetism are interrelated, so current can be induced as well as conducted. So in this case, current is induced, and wherever current is induced, there is always the induction of an EMF. So the first law holds true. Now, the second statement of the same law, or more importantly, we call it the second law, it says that the EMF is given by E is equal to minus d phi by dt, where phi is B dot ds integral. And this phi is given as the magnetic flux through this area. So it's basically the same law, but given in mathematical form. So when there is change in flux, that there is the production of current. And because of current, there's also the production of an EMF. So the EMF E is proportional to d phi by dt, which is change in magnetic flux. And when it comes to the constant for proportionality in this relation, it is experimentally proven to be 1. So this value of 1 is by experimental terms. So when Faraday and other scientists, they started experimenting on this phenomenon, they found out that the constant for proportionality between E and d phi by dt is 1. However, they also noticed something, that the EMF acts in the opposite direction. So therefore, the relation is E equal to minus d phi by dt. So the negative sign again indicates the direction of EMF, which is opposite to the direction of the magnetic flux. And we know that magnetic flux is B times A. So however, they used S instead of A. And the reason why it's integral, because in this scenario, there is change in magnetic flux, which is d phi, and that is equal to B dot ds. And therefore, phi on integration, you'll get integral B dot ds. And that's why the formula is like that. So once again, in a closed conducting loop, whenever magnetic flux through the area of the loop changes due to an external magnet or magnetic field, an EMF is produced in the loop, which also means that there is current induced. And secondly, the EMF which is produced is given by E is equal to minus d phi by dt, because since E is proportional to the change in flux and its constant of proportionality is 1, E must be equal to d phi by dt. However, EMF acts in the opposite direction, so therefore E is equal to minus of d phi by dt. And once again, the value of magnetic flux is integration of B dot ds, again because we have the change in magnetic flux is d phi, and that is equal to B dot change in area ds. So that completes Faraday's law of electromagnetic induction. Let's now look at another important law in this field, which is Lenz's law. So we know that the induced EMF is given by the formula minus of d phi by dt. So the EMF acts in the opposite direction. And the statement of Lenz's law states that the direction of the induced current is such that it opposes the change that has induced it. So this statement is according to Faraday's law. So whenever EMF is induced, there will also be induced current. And current and EMF are in the same direction, and since EMF is opposite to the change in magnetic flux, the current will also be opposite to the change in magnetic flux. So therefore, when we draw a closed conducting loop with a galvanometer for measuring the current passing through it, and now we used a magnet, a bar magnet preferably, and you know the flux is changing as we move the magnet closer or farther away. So let's take the case where it moves closer. So what happens is that now the EMF makes sure that the current is produced in the anticlockwise direction, which also makes the area act as a north pole. And when there are two north poles together, then you know the rule: like poles repel. So therefore, the direction of the induced current is such that it opposes the change that has induced it, due to the fact that it produces a magnetic flux of its own, which opposes the change in magnetic flux of the exterior magnet. And this law, although initially not seeming to be it, it follows the law of conservation of energy. So at first glance, you might think that it actually wastes energy, but no, it follows the law of conservation of energy. And the way in which we can do that is, you can see that the magnetic energy produced is getting converted into electrical energy. So the flux now produces EMF, and the EMF also induces current. So current is induced. So the magnetic energy of the magnet is now converted into electrical energy, which flows through the circuit. And also the work done in moving the magnet, that gets converted into heat energy dissipated. So when we do this experiment, then there is some heat which is dissipated from the current coil. So that heat energy is equal to the work done in moving the magnet. So the mechanical energy converts into heat energy, while the magnetic energy converts into electrical energy. So here, energy is not gained or lost. It is only converted from one form to another, following the law of conservation of energy. So once again, let's look at Lenzs law. Again, very important law. The direction of the induced current is such that it opposes the change that has induced it. So in order to find out the direction, it's easy. If you have the flux here, the magnetic field is passing through it, through the loop, so you can use that and use the right hand thumb rule in order to find the direction of the current, which would be if the flux was induced by the current. However, using Lenz's law, we know that the current will be the exact opposite, so as to oppose the change. So when we use right hand thumb rule, we'll get a clockwise current. But since Lenz's law states that the direction of the induced current is opposing the change, so therefore the current is anti-clockwise. And when it comes to a circular loop, anti-clockwise means it's north, while clockwise means that it's usually south. So this acts as a north pole, this acts as a south pole, so that when we are moving the magnet, the poles repel and attract accordingly. Now let's look at induced current, induced EMF, motional EMF, and EMF induced in a rotating conductor in some detail. So using in the Faraday's laws, we have concluded that E is equal to minus of d phi by dt. So over here, the modulus of the value, so the modulus of EMF, is equal to the change in magnetic flux. True enough. Now, according to Ohm's law, we know that I is equal to V by R. Here, the potential difference is basically the EMF, so E by R. And that means that since E is minus d phi by dt, we'll get the value of minus d phi by r dt as the value of the current induced. So induced current. Now, we know that change in magnetic flux happens when the magnet is moved towards a circular coil. However, when we have a rectangular loop and it tries to enter or leave a stationary magnetic field, then there is also induction of EMF. Now, what does this mean? This means that the process of electromagnetic induction is dependent on relative motion. So it can either be the loop that's moving, or it can be the magnet that creates the magnetic flux that's moving. So either way, we can get magnetic induction. So when this rectangular loop, it enters or gets away from a magnetic field, it experiences change in flux. And change in flux means that there is a current which is induced at the boundary of this loop, and there is also an induced EMF. And that induced EMF is called motional EMF. So the formula for motional EMF is BLV. Again, it's derived from the original formula. So over here, modulus of E is modulus of d phi by dt, which is equal to, in this case, there is change in area. So in delta t, the rectangular loop covers an area covers a length of delta x. So the decrease in area is minus of length times delta x. And since the magnetic flux is B dot A, so it'll be B dot L dot the change in length. I mean the change in x, so it'll be dx by dt. And dx by dt, change in position with respect to time, gives you velocity. So therefore, the motional EMF, E has the formula BLV. And when it comes to current, then if we have a conductor in here, then we'll have internal as well as an external resistance. So I will be equal to BLV divided by capital R plus small r. And this is again using Ohm's law. And over here, the small r is given as the resistance of the rod moving with velocity v in the uniform magnetic field. And capital R is the resistance which is already present inside the loop, inside the magnetic loop, the rectangular conducting loop. So then we have EMF, which is induced in a rotating coil, which is again similar to BLV, but over here we have angular velocity. So V is R omega. Again, we use L in this case, so L omega. So the EMF will be equal to B L square omega. So B omega L square. So the EMF is given as half times B times omega times L square. Omega is angular velocity. Now, let's look at what is eddy current. Now, we've heard of currents flowing straight through a coil, a conductor, but when it comes to electromagnetic induction, there are also forms of eddy currents which are formed. So these eddy currents are basically induced currents, and these are found in conductors when subjected to a change in magnetic field, magnetic flux. So when there's a change in magnetic flux, the current that is formed is in the shape of eddies. Now, eddies are those round motions that water undergoes when it's agitated. So we have patterns of eddies formed of current. Now these eddies are similar to the eddies in water, hence the name eddy current. So eddy currents is induced when magnetic flux linked with the conductor, it changes. So in some cases, eddy currents is good, but in other cases, it's not. It's due to the fact that eddy currents, they release heat energy. So when it comes to applications with heat, such as heater coils or say irons, etc., then eddy currents are really useful. But when it comes to other aspects such as say AC generators, then the presence of eddy currents will not be very useful. So eddy currents are usually removed by cutting slits into the plain conductor. So when we have a plain conductor and we cut slits into it, then the area of eddy currents is reduced, which thereby reduces their effectiveness. This is usually found in copper, so eddy currents in copper plates are usually removed by adding grooves and slits into the copper plate itself. And eddy currents, again, they release a lot of heat energy, and therefore they're very useful when it comes to heating, and it also used in magnetic brakes. So trains, they have magnetic brakes which use eddy currents in order to stop the train. Now let's look at self-induction. So what is self-induction? Current produced in a coil due to change in flux of magnetic field in the same coil. So that phenomena where the current is produced in a coil due to a change in flux of magnetic field in the same coil. So we have a coil, though this is a solenoid, let's just do a normal coil. So current is flowing through it, and again, it is subject to a change in magnetic field by itself. So due to the current or due to something else, there is a change in magnetic flux again, but the reason is due to the conductor. So the conductor itself changes the magnetic flux around it, which leads to more current produced. That is known as self-induction, the phenomena in which current is produced in a coil due to change in flux of magnetic field in the same coil is called self-induction. So if we have a solenoid of n turns, we have flux that is phi will be equal to B dot A. So again, we use integral B dot ds, where ds stands for change in area. So a solenoid has n turns. The value of phi here is for just one turn. So therefore, the EMF, which is induced between the two ends of a solenoid, that will be equal to minus n times d by dt of integral b dot ds. So again, d phi by dt. So EMF is change in magnetic flux times the number of turns, which is capital N. And when it comes to self-induction and self-inductance, the final formula will be minus L dot di by dt, where minus L is the quantity known as self-inductance. It is the constant of proportionality. But more on that on our next segment, which is self-inductance of a long solenoid. So self-inductance and mutual inductance are phenomena that happen in the coil. So self-inductance is when the coil is getting induced current due to its own action, and this happens basically in solenoids. So now we'll learn about self-inductance of a long solenoid. Now, we know that E is equal to minus L times di by dd. Again, that formula will be equal to mu naught n square pi r square L dot di by dt. So therefore, the value of L, which is self-inductance, is mu naught n square pi r square L, where n is the number of turns per unit length of the solenoid. The phi is flux, which can be written as mu naught ni times pi r square, and the r is the radius of each loop of a solenoid. So each of these has a radius r. And inductance is which is represented as L, has many things in common with another unit, which is capacitance, C. And it also has some kind of relation with R, which is resistance, but the complex relation between these three is explored in the next chapter, alternating current. Now, when we have an LR circuit, which is the, a circuit with an inductor and a resistor, then we experience a growth of current, which is defined by the formula I is equal to E by R, which is according to Ohm's law, times 1 minus small e raised to TR by L. T stands for time, R stands for resistance, L stands for inductance, which again can be written as, since E by R is the current due to the resistor, so I naught times 1 minus E raised to minus T by R, the radius of each loop. So inductance basically reduces the amount of current. So basically it's growth of current, but in the opposite direction. So therefore, this will be I naught minus I naught E into raised to minus T by R. And this quantity is known as the decay of current. So it is the value by which the current is getting reduced. And when it comes to energy stored in an inductor, again, inductance is very closely related to capacitance. So the U is equal to half CV square is a formula which is used in the second chapter. And by manipulating, we'll get the formula U is equal to half Li square. So L stands for inductance, which is also known as the coefficient of induction, and I stands for the current or the decay of current. So this is all about self-inductance, where due to one coil, due to the change in magnetic flux, due to the same coil, a coil is getting inducted. However, we can also induct a coil by using the change in magnetic flux due to another coil. So two coils are used in mutual inductance. So that there is a change in magnetic flux in one coil, and there is a magnetic field involved in the second coil. So when we have change in magnetic flux for one coil, the magnetic field is getting induced in the second coil, and that leads to production of current. Mutual inductance is very important because it is this principle which will be used in AC generators, which produce alternating current. So magnetic flux, which is produced here, is defined as m dot I. M stands for, again, inductance, but this inductance is known as mutual inductance, whereas L standard for self-inductance. So phi is equal to mi, which is the direct relation. Now, on differentiating, we'll get the formula d phi by dt is equal to minus m dot di by dt. And what is d phi by dt? That is EMF. So the EMF is equal to minus m dot di by dt. Again, very similar to the earlier formula, E is equal to minus L dot di by dt. Here it's just that the inductance gets changed from L to M because of the way it's getting inducted. Here it's mutual, while in the last case it was self. And in mutual inductance, we have two coils, and magnetic field can be induced in either one of the coils due to the other coil. So we have two formulae for mutual inductance. So in M, so mutual inductance produced in coil 1 due to coil 2 is equal to mu naught N1 N2 pi R1 square into L. And in the other formula, which is mutual inductance produced in current coil 2 due to coil 1, that is equal to mu naught N1 N2 times pi times R2 square times L. So in the other formula, we had mu naught N square pi R square L. So the reason why it was N square, because it was N times N. So it was self-inducted. The coil itself was inducing current. But over here, it's a different coil which is inducing the current. So it'll be N1, N2 instead of N square. And when it comes to EMF, that is induced in the AC generator due to mutual inductance, the final formula is NBA omega sine omega t, which is learned in the next chapter, alternating current, where we will discuss it in some detail. So that concludes mutual inductance. So we looked at self-induction, self-inductance, and mutual inductance. So these are the various ways in which current and EMF is induced in a current-carrying solenoid or coil. Now, finally, we reach rectangular loop. So rectangular loop is one of the most important cases in electromagnetic induction. So we consider a rectangular loop with resistance R moving with a velocity v in a magnetic field. So in this case, the motional EMF that is induced is BLV, and the current due to Ohm's law is BLV divided by R. Now, when it comes to power, in the third chapter, we've learned that power is equal to V squared by R, potential difference squared divided by resistance. Here, the potential difference is E, so E squared by R. So the power that we get is B squared L squared V squared divided by R, thermal power developed in this loop. The magnetic force that we get on the loop is given by the formula B squared L squared V divided by R. So this magnetic force is essentially described as the force which is required to move a loop with the constant velocity. So this loop is actually moving with a constant velocity, and it's escaping or entering into a magnetic field, which produces the induced EMF, induced current, and hence in turn the magnetic force and thermal power developed. So that's why rectangular loop is one of the important cases, because in AC generators, what we do is we keep a rectangular loop, and then we start inducing current out of it in the most basic model. As we reach advanced models, we use two coils which mutually induct each other. So that concludes the chapter Electromagnetic Induction. We looked at Faraday's laws, we looked at induced current, induced EMF, rectangular loops, eddy currents, self-induction, Lenzs Law, mutual inductance, and also motional EMF and EMF induced in a rotating conductor. So these are the most important parts of this chapter. Of course, there are some derivations which are also very important. I recommend you learn them as well. So that concludes this webisode on Brain Blitz audio. So this is a webisode of mind maps. We have a lot of webisodes of grade 12 chapters mind maps. So don't forget to get their link in the description down below. And please also don't forget to subscribe to our channel Brain Blitz Audios for getting more useful information such as mind maps, NEET preparation, memory hacks, learner words, etc. So until the next webisode, take care, stay safe, bye-bye for now.